is based on a lot of information. You've been reading a lot of books, you know a lot about it. Then a few observations will not change your mind very much. Then lambda is very big. This is how much confidence you have in your prior knowledge. But the other way around, if you know almost nothing before, you have no clue, then this will mostly determine, then this will be small. You also see if t goes to infinity, the more and more observations you have, the more and more your belief goes to the observed relative frequency. That makes perfect sense. And that's what people, in statistics, people often work with Bayesian approach, and many feel a bit, oh, the subjective probability, this is subjective. But in the long run, we all converge to what the evidence says. So we get closer and closer to objective, that everybody's agreeing on things. That's what you see happening here. You can interpret this lambda, the weight of your prior information. You can interpret this as number of observations, if you like. This is, this need not be an integer, but let's assume this is 10. Then what you're doing here is just the same as if you had 10 plus t observations, and you simply took the observed empirical frequencies of all the observations. Because if you look a little bit, you can see that indeed, if you have 10 observations with this observed relative frequency, and t observations with that observed relative frequency, the overall relative frequency is this convex combination. So you can just express your belief in your trust of your prior belief. You can interpret that as number of observations. So this is the value of your prior belief. That is equivalent to number of observations, and that is competing with the empirical evidence that you get after. So in a way, everything that makes sense of induction is in this formula. Yes, that's, and prior beliefs is also there, and your trust, because trust is sort of second order effect. It may not be so easy to convince people that you should use it, but it just follows you. So I don't know how you feel about it, but I find it a very pretty formula. This is how inductive reasoning should be. A few simple axioms, and it follows you. You prove mathematically. If you want to set in many situations the axioms are reasonable, and this is what you have to do. So you prove that mathematics are no discussion. Philosophers have long been filling all libraries about how you should do induction. And this kind of, you just, no words, just mathematics. You can't, sometimes they say, you cannot argue with God or with logic. And this is logic. Again, this is a mathematical fact. This is also like Ilke Aydogan, maybe you know he was here. He now is doing very nice work elsewhere. He was a PhD student here. He used this in the decision from experience experiments. And he said, we think in decision from often this is the actions are quite reasonable. Well, no recency effect, okay. If you know how to explain, you know that there should be no recency effect. This causal disjointness, okay. So then, so you can prove mathematically, this is surely in any normative sense, I think, how subject should be reasoning in an experiment on decision from experience. But mind you, here we have this term that many people in decision from experience may not like so much. It is really the spirit of decision from experience that decision from description, they call it prior information, whatever, should not only what we learn from the observations, and the whole philosophy of decision from experience is only what the subject will see during the experiment. That's all the experience they have. That should determine entirely what they do. There's no place in this philosophy for things like subjective prior information, which you might call description or whatever. But then if you prove mathematically that should be part of it, and that's may not always be an easy fit with the philosophy in the field. But I think also, not only mathematically, but also intuitively, if you think about decision from experience, the experiments, the subjects have a lot of prior information, not only what happens if they push the red button. They know this is an experiment from psychologists with money, as there are many experiments. They should not let you lose, so you know the outcome will not be negative. You know the outcome is not going to exceed €1,000 because then you get tax complications. So you already know it's a number between 0 and 1,000. And you know that if you spend the experiment will take half an hour, on average you make between, I don't know, between 5 or 20 euros or so. So subjects do know quite a lot when they enter the laboratory. There is a lot of prior information. They do know that if the outcome is 1,000, the probability is not going to be big. They know that beforehand. So the subjects have a lot of prior information when they enter the lab and do a decision from experience experiment. I think you should incorporate it into your models. And you should also, when you do data fitting and so on, they should be part of it. So Ilke did that. And I think he was the first who really pushed the point. You should look at prior information, also in decision from experience. So it's a quite new thing. And of course, some people had some difficulty digesting that result. But I think it was a beautiful paper that he wrote, and he was using this formula. That's one application. It can be seen, for those of you know about probability and prior distributions, second order distribution, I'm going to say more about it in a few minutes, which is done in the Bayesian approaches, that this means in fact that you have a beta prior. If it's two results, if it's more than two results, then better, sometimes they call it Dirichlet process. This means in fact that you are using a Dirichlet process in your reasoning. So this is a very nice axiomatic justification of using this Dirichlet process. This may become a bit clearer in 10 minutes when I showed you the next result.
Sorry, can I briefly ask you, this only holds if you have at least 3 outcomes?
Yes.
So can you sort of give us some sort of intuition why it doesn't work for 2?
Well, one thing is, maybe you remember this joint causality. If there are only 2 results, then this joint causality is a vacuous condition.
Mm.
And then you lose it, and it turns out that in a moment I'm going to show you another theorem, and then you can even better probably understand that then things get too weak. Then every ID process will do it also, if not beta prior. So that's one way to see that this is. I don't know if you, I already said I find this a very pretty axiom, a very pretty theorem. It is not at all. By the way, Carnap was the first to fully. There's a guy called W.A. Johnson in the 1920s. He already had much of it. He already conjectured results. He already wrote some axioms. He didn't give complete proof. So a little bit it existed before. W.E. Johnson, also a good researcher, but then Carnap really did it. This theorem is not very well known. Very few people know it. This is the prettiest theorem existing. But Carnap, he did not write papers on it. He wrote books with his results. And he did result much more advanced. I told you about this joint causality, but in many cases there is some causal relation. So he had models where one result has a causal relation with the other, then parameters for how strong these causal relations were, and they may change over time. So many complex and general models were in his book. And this was a sort of trivial result for him, so he didn't pay much attention. And then, the books, although they are still cited a lot, but still, it's not so very accessible. And since then, you can't write a paper on it then because it was already existed. I think maybe one of the best services that anybody or I could do to the field is only write this theorem, nothing more, and publish this in a journal so that people are easily accessible. But the rules of the game in academia is you must do something new, so it's a bit of a pity. So that's a bit strange situation why the result is not so very well known. But now I show you another, maybe if this, to me this may be the prettiest axiomatization I ever saw. All the ingredients of induction come out just by, it must be like that. Nice support for Bayesian. Now I show you a related result that is really famous, that many people know. That's a result that De Finetti did. And many of you know De Finetti bookmaking. I teach it in courses, and many of you know it from courses. It's in my book, 2000 book. This is another theorem of De Finetti, another one. This one is more known than the bookmaking theorem that I told you. Although, if you type in Google De Finetti theorem, you get this one, not the bookmaking theorem. But this is even so 2 very famous results. This is now, I'm going to drop, maybe you remember I had 3 axioms. I had positive relatedness, exchangeability, well it doesn't matter, and I had disjoint causality. Now I'm going to drop disjoint causality. I'm going to take only the first 2 axioms, or positive, okay, and exchangeability. And then I'm going to tell you axiomatization, what then is axiomatized. It's a more general thing than what I just showed you. But this is also very useful, a very famous result, sort of basis to Bayesian statistics. So, theorem definitely 1937, first wrote it. Theorem axioms 1, so positive relatedness, and 2, exchangeability, if and only if some form of updating holds true. I'm going to take quite some time to explain what comes here. I can say it in a few words for specialists. If you know an idea in an independent, identically distributed process, whenever this is a mix of ideal processes, that's if and only if those two axioms hold. But I'll be a bit slow in explaining what a mix of ideal processes means. So let me erase all of this. Now I'm going to just tell you what is, I'm going to give you examples. And in the end, when you solve your example, I can tell you that this is all that exists. So a first example of a way of updating beliefs that satisfies those first two axioms. That's example 1. That is, if we just take one ID process, you know, independent, identically distributed, a very common abbreviation. It goes like this. There exists a probability measure Q on a set of results and the process is ideal. That means if you the probability of result I, if you have a set of evidence E, it is just the prior probability, if I can call it that way, just like that. So your beliefs don't change. You already know the probabilities. Maybe you know really it's a fair coin. No matter how many heads and tails you keep on believing it's a fair coin. Something like that. So this is a very simple example. Now, in this example, the positive relatedness holds true. Well, it's 0. Maybe you can discuss that. Exchangeability also holds true, because the order of if you have a sequence of observations, the probability of getting that sequence doesn't depend on the order. It depends only how many times, 1 or 2. That's how many times the probability appears in the product. So exchangeability is clearly satisfied. So this is the first very simple, maybe degenerate example, and not so interesting. You're not learning anything here. Everything is already known up to probability. Now, example 2. Is a mix of two ideal processes, 50-50 of two ID processes. It goes like this. We have Q1 and Q2 are two different probability distributions over the set of results. And you know there's a 50% chance that the whole process it goes by Q1, just independent repetitions of Q1. And also there's a 50% chance that the whole process go by Q2, independent repetitions of Q2. So maybe you could imagine that you have a coin and you know it's not completely fair. Let me write a bit. Maybe, so an example of this, there's a coin. This is more realistic than you may think. Let's say Q1 heads is 0.51 and Q2 heads is 0.49. So maybe you know that the coin is not entirely fair, but you don't know what the bias is. Maybe heads a bit more, maybe a bit less likely. That means that a priori, your subjective probability of heads is 0.5, because you don't know over under stage is 0.5 a priori. But if you think a little bit, what happens if you make a few observations, although conditional on the Q1 or Q2, their observations are independent, in reality they are not. I don't know, imagine it is like this, and imagine the coin will be flipped 2 times, and now you can gamble. Either you get some very big amount of money if the 2 results are the same, or you get a very big result, a big amount of money if the 2 results are different. What would you prefer? If anybody?
The same.
The same. Why would you prefer the same?
Because if it's one outcome in the one, then you update that it must be the one.
Exactly.
Yeah.
It's a bit. That's the easiest way to see it. Imagine the first toss gave heads, then your conditional probability on heads the second time is bigger than 0.5, because the first observation being heads mean that Q1 becomes a bit more likely than Q2. So therefore, then it's good to gamble on heads. And if the first observation is tails, then it's good to gamble on tails the second time. It's the same story. So that means if a coin, if it's like this, 2 same results are more likely than 2 different results. That means in that sense, the results are not independent. And in general with coins, if you don't know, also if it's more complex mix, if you must gamble with coins, repeat it, always repeat on with the same result, not on different result, because this holds quite generally. That same result is more likely. Although if you're trained in only in objective probability, you think it's 0.5 and independent, so it doesn't matter. Well, it doesn't matter. If you have this subjective philosophy that many Bayesian and the Finetti like so much, then it does matter. So this is an example. And anyway, in general, if this is any, it can be many outcomes, not only had. By the way, this theorem I'm telling you now also holds true if there are only 2 results. Because this distant causality is dropped anyhow, that was a critical thing for 3. Anyway, if you have quite general results and quite general probability distribution, and then if the process proceeds, in the beginning, your prior probability, if I'm using the term now for these things, anyway, these are 0.5, 0.5. But if you made a few observations, maybe imagine that if this is colors from an urn, and Q1 says red is very likely, and Q2 says red is very unlikely, and if you made a few observations and red occurred a lot, then after that you say Q1 is, now I believe much more that it is Q1 process than that it is the Q2 process. So you update these probabilities depending on your observations. And you can feel that you must do it, but the base formula is just a formula you can calculate if it's complex to write, but it's simple to understand that you do that. So after a number of observations, the probability of it being this or that process is changing, it is updated, and therefore, of course, also the probabilities over the outcomes change, are updated. And that's how the process works. Well, this was example 2, maybe I could say example 3. Oh, by the way, maybe one more thing to say. I hope you can see that what positive relatedness is satisfactory, but also exchangeability. Because if you have a sequence of observations conditional on Q1, the order does not matter. Conditional on Q2, the order does not matter either. And the real probability is just a 0.5 mix of those 2. So this process is still satisfying exchangeability. And that's how exchangeability is generalizing independence. Okay, another example, I could call it example 3, would be like example 2, only maybe it's not 50-50, but maybe this is probability 1/4, maybe with probability 1/4, it's Q1, with probability 3/4, it's Q2. Any mix of 2 ID processes, and everything, nothing really changes, you know. The exchangeability is still satisfied. So these are other examples. And in fact, it need not only be a mix of 2, it can be any mix. You can take the set of all probability distributions over the outcomes. You can take any second order probability distributions over those probability distributions. That gives you a mix of IID processes, and that is still satisfying exchangeability by reasoning the same way as I showed you before. You can really see it. So indeed, all mixes of IID processes satisfy exchangeability and also positive relatedness. And it turns out that that's the only, the theorem that I showed you, axiom 1 and 2 hold if and only if what you are doing is a mix of IID processes. So Davinati proved that in 1937, and that was a big result that gave a big boost to Bayesian statistics. Because in statistics, this framework that you say we have some observations, we have a probability distribution over it, but we don't know it. What it is, that's a common framework in statistics. Then you parameterize the problem and you say, I don't know this parameter. Anyway, and then Bayesians say, we think that you should express your uncertainty about what the true probability distribution is by means of a second order distribution over the probability distributions, and then you should do Bayesian updating. That's what the Bayesians like so much. And the non-Bayesians, they have all kind of objections against it. But such a nice theorem quite supports it, you know. Okay, there's also quite some Bayesian in it by saying that the probability of the results must be expressed in terms of subjective probabilities. That is really less controversial than these second order distributions, but that's the only thing. After that, exchangeability, you know, who can object against exchangeability? You know, in many situations, it's a quite common assumption in statistics that exchangeability is satisfying. Well, then you have to do what the Bayesians say. This controversial thing of the second order subjective probability distribution over the unknown first order probabilities, it just is proved mathematically. So this axiomatization of Davinati is very influential and famous. And it's a sort of a generalization of Carnap, you could say. Now, so I told you that any mix over such things can happen. That mix is a second order distribution over first order probability distributions. And then Carnap is a special case where that second order distribution is like the Bethe family or the Dirichlet process. So in that sense, Carnap is just a special case of what Davinati did here. So that's how those things are related to each other. And well, maybe let me only say in words one funny experience I had in 1989. Most of you were not born yet, but I visited the US for a year. And there was Hervé Moulin, maybe some of you may know Hervé Moulin. He's well known in social justice theory, welfare theory, voting theory, and writes axiomatization. It's quite well known. He had just published a paper. It was in fact the Carnap formula, but formulated for cost division, I think. So the idea was that a group of people have to pay something, jointly they have to pay, and everybody has a commitment, an individual commitment to paying a particular part. But if you add it up, it may be more or less than the total, so they have to agree with each other who pays how much more or less. Then he formulated, in fact, this joint. He said how much a person has to pay depends on how much his individual commitment is and how much the total commitment of all the others is. But it does not depend on how, if the others one pay more or less. That's the only thing that matters for my formula. That is like joint causality. And he just wrote the same formula. So I visited him and I told him this thing that you just discovered and published. I already knew it 5 years ago when I was a PhD student. That was my opening sentence by meeting him.
That was also the last sentence?
No, he was nice. I told him Carnap, and then he, first year, well, how can you say? Then I explained to him this Carnap thing, and of course it exists. Then he liked it much, and we had lunch many times, and I learned many things from him. So, well, it was a nice way to open the meeting. Okay, so that's the end of my presentation. So now you will all be Bayesian from now on, right?
Yeah.
Very good. Any questions? Okay, well, then we can go for lunch.